In this podcast, we'll use the equation of a rational function to tell us all of the main properties. Again, it's helpful to factor the function completely to help us see all the different properties for these rational functions. In the numerator, I see 4 terms. I would try to use factoring by groups there. That's our main technique for when we have multiple terms, like 4. We can factor an x squared out of the first part, and what's left over should be an x plus 5. And for the second part, we can factor out a negative 9, and what should be left over is x plus 5. So it tells us the numerator factors into x squared minus 9 times x plus 5. But the x squared minus 9 difference of perfect squares, so we can factor that further into x plus 3 times x minus 3 times x plus 5. For the denominator, it's a quadratic. The product of the factors is 3. The sum is 4. So x plus 3 times x plus 1 should factor the denominator completely. Now that we have it factored completely, we can check to see if there's any holes in this graph. In this case, there is a hole because we have this repeated factor at x plus 3. So the x-coordinate of the hole should be when x is negative 3. To find the y-coordinate of the hole, since it's just one point missing from this graph, we can basically plug in negative 3 into the rest of the graph. We get negative 3 minus 3 times negative 3 plus 5 all over negative 3 plus 1. So that should give us negative 6 times 2 all over negative 2. Or the point for our hole should be when the x-coordinate is negative 3 and the y-coordinate should be positive 6. Again, once we have the hole discovered, we basically want to remove that common factor and look for the remaining properties in the remaining piece. We want to just concentrate on the remaining terms to see the properties. So after I've removed the x plus 3 factor, I can find the zeros by looking where the numerator is equal to 0. This should have a x-intercept at 3, 0 and at negative 5, 0. Vertical asymptotes are where the denominator is equal to 0. So there should be one at negative 1 for this graph. And then to see the end behavior, whether I have a horizontal asymptote or a slant asymptote, again, it's helpful maybe to look at the degrees of the terms. I could use the original function, but since I've already removed this hole, it might be helpful just to look at the multiplied out remaining piece. So the numerator, I should have x squared plus 2x minus 15. The denominator, I have x plus 1. Since the degree of the numerator is 2 and the degree of the denominator is 1, the degree of the top is 1 more than the bottom. That tells me I do not have a slant asymptote, but I do not have a horizontal asymptote, but I will have a slant asymptote. And to find the slant asymptote, this is where I could use synthetic division here since it's just a degree 1 term on the bottom, but I can always use long division and divide out looking for the non-remainder piece. So let's divide out. X goes into x squared x times. So multiplying x times x plus 1, I should get x squared plus x. Again, my division algorithm says to subtract that polynomial. So x squared minus x squared leaves nothing there. 2x minus x should leave me just an x left over there, and I can bring down the next term. I'm left with an x minus 15. Well, in order to multiply to get x, I can multiply x plus 1 times 1. So I should get x plus 1. I can subtract, and I'm left with negative 16. Since now the degree of this last piece is smaller than the degree of my divisor, that tells me my remainder should be negative 16 over x plus 1. When I have a slant asymptote, well, this remainder piece gets very, very negligible on the very far left and right of the graph. So to see what the slant asymptote looks like, it's just going to be the whole part from the long division. So it should be looking like the graph y equals x plus 1 on the far left and far right. I can use these properties to then help me graph this function nice and accurately and see all the main features.